I'll be using a school of Swedish fish as a case study. Here we see a school of 50 fish made up of 18 red fish, homozygous for the dominant A allele, 24 orange fish with a big A allele and a little A allele, and 8 yellow fish, homozygous for the little A allele. In order to determine if this population is in Hardy-Weinberg equilibrium, we can start by finding the genotypic frequencies of the population by dividing the subpopulation of each genotype by the total population. This gets us 0.36 for the big A, 0.48 for big A, little a, and 0.16 for little a. Now that we know the genotypic frequencies, we can find the allelic frequencies by taking the total number of each allele and dividing it by the total number of alleles in the population. Doing this gets us 0.6 for the frequency of big A alleles and 0.4 for the frequency of little a alleles. Finally, in order to determine if the population is in Hardy-Weinberg equilibrium, we can denote the frequency of the big A alleles as P and little a alleles as Q. Next, we must plug in both P and Q into the equation and obtain a value of 1 for the population to be in equilibrium. After plugging in these values for each allele, we obtain 1 as a result, which proves that the population is indeed in equilibrium. I'm now going to talk about a selection event that affects the school of fish. These fish live within a dense red-colored kelp forest, depicted by the red-colored page. When large-scale candy fishing begins in this region, the population is altered, and the red fish are left untouched, since they blend in with their environment and are impossible to spot. The orange fish are easier spotted, and the yellow fish cannot camouflage at all, and are therefore the easiest spotted. This drastic change is the Hardy-Weinberg equilibrium violation of selection, in which different genotypes have different abilities to survive and reproduce. This can be quantified by fitness values. In this situation, since the red fish are unaffected by selection, their fitness values would be 1.0. The orange fish have a fitness value of 0.8, and the yellow fish have the lowest fitness values of 0.6. In order to determine to find the genotypic ratio, we would first need to take the pre-selection frequencies of each genotype and multiply by their respective fitness, which yields us unadjusted post-selection frequencies. Next, we would divide these unadjusted frequencies by the average fitness, which can be calculated by taking the sum of unadjusted frequencies. The resulting values are the frequencies after selection occurs of each genotype, in order to determine the allelic frequencies after selection as shown here. The resulting frequencies of the big A allele is 0.67 and the frequency of the little a allele is 0.33. Based on the frequencies of the alleles post-selection, it is evident that directional selection is occurring, since the frequency of the big A allele increased and the little a allele frequency decreased. In our case, selection favors phenotypes that are able to effectively camouflage to avoid detection from fishermen. In the future, the population will shift towards becoming more and more red phenotypically, since this color provides the population protection from fishermen.